Okay, thank you so much. Our speaker today is Dr. Jessica Werk of University of California, Santa Cruz, my old haunt as well. She has a Bachelor in Arts in Astronomy and Physics from Wesleyan University. Her PhD is from the University of Michigan. She's currently a Hubble postdoctoral fellow at UC Santa Cruz, which, if you're not aware, is one, if not the most highly regarded postdoctoral fellowship in astronomy. Her observational experience, she's an observational astronomer. It spans the electromagnetic spectrum and includes a plethora of ground-based, kind of very impressive a list of ground-based and space-based telescopes. Let's give a warm welcome to our speaker, Dr. Jessica.
Wow, thank you. Thank you all for coming to my talk. So, what you see here, pictured on the screen, is probably one of the most prominent features of an actual dark night sky, if you're ever fortunate to experience one. And it's probably been contemplated since anyone was ever able to contemplate anything. And what we now understand, after centuries of research, is that the Milky Way starry disk, visible with the naked eye and through optical telescopes, spans over 100,000 light years. Encircling that is a disk made of mostly hydrogen, visible with radio telescopes. And engulfing that is an enormous halo filled with warm, hot, 100,000 to million degree Kelvin gas, and of course dark matter, which cannot be detected directly. The Milky Way is so huge that dozens of lesser galaxies circle around it, slowly getting cannibalized by the Milky Way. And of course, also a result of its size, the Milky Way boasts at least one planet with intelligent life on it that can think about it and contemplate it. So as Scott mentioned, I am an observational astronomer. I study the gas in and around galaxies. And in order to introduce my research to you, and in particular a survey that I've been closely involved with, I'm going to provide you with quite a lot of background. And so I'm going to review some relevant extragalactic astronomy, a little bit of history, and then I'll get into some key concepts on a particular field that I study. And then I'll finally introduce the survey to you, and one of I think my most important results and contributions to the field in solving kind of a long-standing problem in galactic evolution. So, like I said, if you're fortunate enough to experience a dark sky, the Milky Way is really a thing to behold. And sometimes I try to imagine myself stripped of all astronomical knowledge and looking at this stripe in the sky. And I wonder if I would be able to deduce what it is. And in a way, when I do that, I start to feel a little bit like a meatball in a plate of spaghetti or something. It's hard when you're inside of something to really understand its structure, its size, its composition. So it turns out that the first person to resolve the Milky Way into individual stars was Galileo, with his 1.5 centimeter refractor telescope. And of course, early astronomy, philosophy and astronomy are inextricably linked, and I think Kant is given credit, at least, for being one of the first philosophers to propose that the Milky Way was a rotating body of stars with a disk-like structure, and that the nebulae observed in the sky are separate island universes, kind of like the Milky Way. But of course, this debate, it became clear in the 1920s that this debate could actually be resolved scientifically. And so now, instead of 1.5 centimeters, telescopes are 100 inches, and you can start to resolve these fuzzy blobs or nebulae. But still, in the 1920s, there was quite a lot of debate. And I mean, I think it's amazing to think that only 100 years ago, we were wondering if our galaxy, if what is the size of our galaxy is the same question as what is the size of our universe. Okay, people actually thought that these nebulae could be at the outer ends of the galaxy, and the galaxy could just be a large place like our universe. It turns out that in 1925, Edwin Hubble and settled this debate by determining very precisely the distance to one of these fuzzy nebulae, our nearest neighbor galaxy, the Andromeda galaxy. And so he's called the father of extragalactic astronomy for this reason. And so how did he determine the distance to Andromeda? Distances in astronomy have been one of the most important or fundamental things. I mean, how far away is this thing that we're looking at? And so how did he deduce that? Well, there are a couple things that you need to know and appreciate before you can appreciate that. So in particular, the apparent brightness and the intrinsic brightness of something are related to each other inversely proportional to the distance. And so if you want to know how bright something is intrinsically, if everything were at the same distance, its luminosity, you would need to know its distance in theory, okay? And then you would know its apparent brightness, and you could relate the two. And so the thing is, you can't just know something's intrinsic brightness unless you know something fundamental about the way that it physically operates, or you use something closer to calibrate it. And so Henrietta Leavitt in the 1920s worked fervently to catalog a type of variable star called a Cepheid variable, and determined that these stars, that there's a relationship between the rate at which they vary their apparent brightness, this period, and their intrinsic brightness, their luminosity. And by determining this fundamental relation, this period luminosity relation for this particular kind of Cepheid star, Hubble then used the Cepheid variables visible in the Andromeda Nebula at the time to place a precise distance on it that put it well outside any estimates for, what the size of the galaxy could be. And all of a sudden, extragalactic astronomy was born. Now, there's not just two galaxies in the universe all of a sudden. There are lots of galaxies in the universe. And one of the things, another thing that Edwin Hubble contributed to the field is he determined that not only are there other galaxies, not only are the galaxies moving away from us, but the more distant galaxies are moving away from us at faster speeds. And so the way that he figured this out is if you take a spectrum of a galaxy that has dispersed its light over many energies or wavelengths, you can identify certain features in the spectrum. And these are features the result of absorption from specific chemicals that are in the interstellar medium of galaxies or from the stars themselves, and their signatures, right, in the spectrum. And then you look at the spectrum of an actual galaxy, and they're redshifted. And this is the same as Doppler shift, if you know what that is. Something's moving away from you, the frequency changes as it's moving away. It gets longer, it's a redshift of light. It's the same concept. And so galaxies' absorption features or emission features are redshifted. You can measure the degree of this redshift, ultimately get a velocity at which they're receding from us. You know the distance from the Cepheid variables in them, and you can get a relationship between the distance and the velocity and determine that most galaxies are moving away from us, and the more distant ones are moving away from us faster. And of course now we have the Hubble Space Telescope after Hubble, and we've been able to determine this law, Hubble's law, with even greater precision using other standard candles. The Cepheid variables are called standard candles. And so redshift is now an indication of how far away something is. And so 100 years later, we find ourselves able to image galaxies with these island universes with an unprecedented resolution. And so here are some more lovely pictures of galaxies. These galaxies are very distant apart from our own Milky Way, and what we understand is that the Milky Way is just one of billions of galaxies in the observable universe. And I particularly like this image of the Hubble Deep Field, which I'm sure you've seen before. And this was many, many hours of integration of exposure time using the Hubble Space Telescope. In this field alone, there are more than 3,000 galaxies. And it's equivalent on the night sky, if you were to take a grain of rice in your hand, hold it at an arm's length up to the sky. That's the area of the sky that this image probes, a grain of rice at an arm's length. And so this image alone has 300,000 galaxies. The Milky Way is one of billions of galaxies in the observable universe. So galaxies, what we understand, come in all shapes and sizes. This is another extragalactic indicator named after Edwin Hubble, the Hubble tuning fork diagram. And you can see some galaxies are more elliptical in nature. These galaxies tend to be older. They're not forming new stars. And some galaxies have these beautiful spirals. Some have bigger bulges and smaller bulges than others. One of the things that we know now as astronomers is that galaxies come in several shapes and sizes, but they're pretty dichotomous. There are red galaxies and there are blue galaxies. And the way that they're divided is, they're not forming stars anymore, or they're forming stars. The red galaxies are thought to be old and dead. I mean, they're not technically dead, but they're not forming new stars at the same rate as their more beautiful counterparts, blue counterparts. So that's something to remember. And of course, the tools of the trade have really improved immeasurably since Galileo's 1.5 centimeter refractor. And so it turns out that you can understand a lot of what's going on within a galaxy and outside a galaxy by looking at it through many, many different wavelengths. And you can understand different physical processes like young stars or gas around galaxies, dust in galaxies. And galaxies, of course, are not just static, beautiful jewels in the sky. There are complex processes happening within them on a regular basis. And the stars in the galaxy are fusing the building blocks of life. And so this is just a very simple picture of what's happening in the interstellar medium of galaxies, but this is something I'll refer back to. By some magic, stars form. The stars themselves, it's not really magic. I'm just putting a whole subfield of astronomy into one sentence. What stars do is they fuse elements together. So hydrogen ends up fusing into helium. Helium ends up fusing into carbon, and then nitrogen, and then oxygen. And so you slam atoms together, you get energy released. And what we call, there's some terminology that I'm probably going to end up using, so I figured I would point it out now, is heavy elements. We call metals anything heavier than hydrogen and helium. And so actually I wrote, my first paper that I wrote was called the metallicity of NGC 2915 or something. And my mom wanted to read it because she was really proud of me. It was my first paper. And she read the whole paper. It's something that's peer-reviewed in the Astronomical Journal. And she said afterwards, she's like, okay, but I have one question. I was like, wow, you have one question, just one. And she was like, is oxygen a metal? And so, yes, in astronomy, oxygen we call a metal. Okay, so now one of the things I want you to keep in mind, I'm just going to review structurally the different components of a galaxy. So you have a picture in your head, like I do. I'm putting a black hole in there for black hole enthusiasts. Okay, so we've got your galaxy, you've got galaxy disk. This is where a lot of the action in a galaxy happens, a lot of the star formation. This is in light years, 100,000 light years. If you think more in kiloparsecs, a good number to have in mind is maybe like 20 kiloparsecs total. And so the halo, actually there's new research going on halo stars, which extend out to 50 kiloparsecs, so they would be probably off this image. But the halo stars tend to be older stars. Globular clusters are very old relic things from early galaxy formation. You've got a bulge of a galaxy. And then, of course, not pictured are some of the things about the components of a galaxy that I'm going to be talking about. In particular, the dark matter halo of a galaxy. And this extends over 10 times the observed optical radius of a galaxy. And we can't see it directly, but we know it's there from a variety of observations. This matter interacts gravitationally with normal atomic baryonic matter, but not electromagnetically or in any other ways that we can deduce so far. And so, but one of the things that I'm showing here is one of the classic ways in which you can measure the dark matter content of a galaxy, and that is to take a rotation curve of the galaxy using something like the hydrogen gas encircling the luminous disk. And what you see is that it doesn't drop off as you might expect for something that had a more central mass distribution. Instead, it flattens out as if the mass beyond the optical radius of a galaxy continues. And in fact, there's more mass beyond what we're observing. So dark matter halos, we'll talk a little bit more about this, but they contain most of the mass in the universe by far. So dark matter, the dark matter component of a galaxy, is far more massive than the luminous matter. And I'll talk a little bit more about that more specifically. And then, of course, very, very recently, and I would say only in the last 5 years, have we begun to appreciate that there's yet another component of a galaxy. And this is the diffuse gas that fills the dark matter halo of the galaxy, which I'm going to call the circumgalactic medium. And it's actually, by mass and volume, the second largest component of a galaxy. And I'll talk a little bit about why it took so long before we were able to actually observe it and really understand that it's a ubiquitous thing in a galaxy. And of course, I'm going to talk to you about one survey that I have that probes this fairly elusive medium. But in order to, I think, appreciate a galaxy or the circumgalactic medium, I think it's important to understand that galaxies are not quiet, uneventful places. Most are born out of violence and live in a constant state of turbulent complexity and upheaval. There's gas falling onto a galaxy, gas coming out of a galaxy. There's all sorts of mergers happening. There's satellite galaxies around a galaxy, but you've got all these processes happening beyond what you can see with your eye, beyond the beautiful spiral disk of a galaxy. There are processes like feedback, wind-related feedback, where galaxies are driving these large-scale winds, containing a ton of energy and mass, into their outermost parts. And not only that, this gas is falling back down onto a galaxy in what's called recycling. And not only that, but there is gas out here in the intergalactic medium that's falling onto the galaxy. There's gas that we observe in the halo of a galaxy that's going to ultimately fall onto the galaxy and form new stars. So a galaxy, it's a dynamic place. And these two processes, the winds and the accretion, end up mediating galaxy evolution. They're fundamental for the existence of a galaxy. And basically, they're inextricably linked to the existence of this circumgalactic medium. The circumgalactic medium is where all these processes meet, where wind ejecta from a galaxy meet accreting gas, and where satellites are stripped and disrupted, and where this gas may eventually be recycled. And so it turns out that without directly observing gas falling onto a galaxy or gas coming out of a galaxy, we know that they have to play a large role in shaping the properties of galaxies from several fundamental relations. And I could probably give you snapshots of a bunch of these, but some of the most relevant ones are this baryonic dark matter relation. So bear with me here, I'm going to explain this plot that I drew. So basically, we know from several experiments, Big Bang nucleosynthesis, the cosmic microwave background, that there's a very precise ratio of baryons to dark matter in the universe, and that is 0.17, right? 17% of all the gravitating matter in the universe is baryonic or atomic, a normal atomic matter in nature. And now, so this particular fraction is represented up here by this dotted line. And so, but when you take galaxies themselves and you add up the stars in the galaxies, it turns out that the baryonic mass of stars related to the total dark matter mass is far less than this known fraction of baryons to dark matter. And so, in simpler terms, what this means is galaxies are baryon poor compared to the cosmological average of baryons. Galaxies, their baryonic fraction, if you're just to take into account the stars in the dark matter halo, is about 5%, right? And the cosmological fraction is 17%. So where are these baryons? People use this missing baryon problem of galaxies. They say that, well, galaxies have probably ejected a lot of their baryons, or maybe they've never fallen in. But in any case, this is a fundamental thing that I think probably requires some inflow and outflow. Now, I mentioned before that the galaxy population is fairly dichotomous in nature. There are blue galaxies, there are red galaxies. There are green valley galaxies too that people talk about, but anyway, the universe has two types of galaxies, star-forming and non-star-forming galaxies. It turns out that when you study the population of galaxies over time, right, over redshift, higher redshift means you're looking back in time, so it's earlier times in the course of the universe. At earlier times, there aren't very many red galaxies. In fact, this red sequence ends up building up toward present-day times. And so what this tells us is that some fraction of the blue star-forming galaxies evolve into non-star-forming galaxies. They have their star formation quenched. This is what people like to talk about. This is quenching. And so how this happens, ultimately, we think is fundamentally related to this dynamically evolving balancing act between gas supply and gas consumption in galaxies. So, and finally, just in general, one thing to remember is that there's a fundamental relationship between the star formation rate of a galaxy, that is how fast is a galaxy making new stars, versus how much gas it has. You need gas to make stars, right? This relationship is well studied, well known. Here's the simple power law. The more gas you have, the more stars you form, right? Well, the Milky Way has a certain amount of gas and has been forming stars at about 1 solar mass per year. One new sun every year, the Milky Way's churning out. And so that's all nice and good, but we think that it's had that star formation rate for billions of years. But at that particular star formation rate, it would use up all of the gas that we know is there too fast. And so what that means is that new gas has to be falling onto the Milky Way to replenish the supply of fuel so that it can maintain its star formation rate, which has been fairly constant over its history. Now this is averaging out over a lot of things, but fundamentally I think it's true. And of course, there are also direct observations of these phenomena. I think they're probably some of the most lovely images. Our Milky Way itself is driving a huge amount of material into its halo. And so what I'm showing you here are what's called these radio lobes. They're tracing the Fermi bubbles, which are observable through gamma rays, if you're familiar with that. And these are giant magnetized outflows from the Milky Way. And they're star formation driven, they think, although they could be from some interaction with the black hole at the center of the Milky Way. There's some debate as to whether or not it's from that. But it's driving a huge amount of material into the halo. And of course, in the Milky Way disk itself, there are observations of galactic chimneys, these sorts of features in the hydrogen gas, these high latitude H1 clouds indicating that gas is actually leaving the galaxy at a fairly fast rate. In other galaxies, there are some incredible pictures that we have in X-rays, in excited optical emission, in dust traced by infrared light, and molecular gas flowing out of all galaxies, basically. These outflows, when you look at a large sample of galaxies and you look really deep at the galaxy, or you take a spectrum of it, you find that nearly all galaxies, at least all galaxies that are actively forming stars, are driving large-scale winds. And the rate at which they're ejecting gas is actually the same rate at which they're forming new stars. So there's some kind of balance between stuff that's coming in, stuff that's going out, and the ongoing process of star formation in a galaxy. And of course, galaxies are actually accreting gas. Direct observations of gas accretion in galaxies are harder to come by. But in particular, there are a few. So I don't know if any of you have ever been to the southern hemisphere, But when you look up at a dark night sky from, say, a mountaintop in Chile, you can see some of very prominent features in that sky are the Magellanic Clouds. And these are two dwarf galaxies getting cannibalized by our Milky Way. They're in the halo of the Milky Way galaxy. They're filled with H1 gas, hydrogen gas, and this is a map of their gaseous content. Now, this is a huge amount of fuel. Ultimately, these things will fall into the Milky Way. They'll provide 10 to the 8 solar masses of gas, of new supply fuel to the Milky Way. And there's also this is the whole Milky Way sky in H1. Here are the Magellanic Clouds that I mentioned. The Milky Way is on the plane here. And what you can see is there's a huge amount of H1 in our halo. We don't know exactly how far away it is. We actually think this map's more of the inner halo. But in any event, these clouds have a kind of head-tail structure. And like they're moving toward the Milky Way, right? Like they're moving through some kind of hot medium toward the Milky Way in these head-tail structures. And so this is evidence that the Milky Way is actively accreting gas. And so where these two processes meet, these outflows and these inflows, is where I come in. And I want to look at this gas. I want to look at it out to distant radii. But there are some impediments to studying this gas. It's not very easily observable. But this gas is highly ionized. It is hot. It is over 10,000 degrees Kelvin, and it is very, very diffuse. So now I'm going to get into some of the halo gas concepts. So why is it so hard to see? So in the Milky Way, there's gas that's about 10,000 degrees Kelvin. It's forming new stars. It's ionized gas. Its density is about 100 atoms per centimeter cube, per cube centimeter. Okay? Now, the gas that we see in the halos of galaxies is about the same temperature, but its density is about 10 to the minus 3, 1/1000th of an atom per cubic centimeter. So it's 1,000,000 times less dense than the gas that's, around the new stars forming in the disk, 1,000,000 times less dense. That also translates to not very much surface brightness, very difficult to detect directly. And so another impediment is that at these temperatures, you have to look in the ultraviolet. And you can consider this a fortunate thing or a not so fortunate thing, but our atmosphere blocks ultraviolet light, luckily for us as living beings. But unfortunately for us as astronomers who want to study the ultraviolet, we have to send spacecrafts above the atmosphere in order to look at the light at this particular temperature or energy. And so one of the ways that you can study, there are several ways you can study diffuse gas, but like I just said, it's very, very diffuse. And so the thing that I do is I use absorption spectroscopy. And so the principle is the same as just a general principle of spectroscopy, where you've got a bright background source, you've got a cloud of cooler gas that's very diffuse. The light from that background source passes through the cloud and produces a sort of signature absorption spectrum. Absorption lines that correspond to transitions, atomic transitions, corresponding to the chemical composition of the gas and temperature and density and all of these physical properties of the gas. And so instead of a light bulb, I use a cosmological light bulb called a quasar. And so quasars are nice because they can be seen over very vast cosmological distances. They tend to inhabit the centers of very active young galaxies. They're indicative of an active galactic nucleus or a very active black hole in the center of a galaxy. They're probably some of the most luminous or energetic objects known in the universe. They emit up to 1,000 times the energy of the Milky Way itself. And so the Milky Way contains the energy output of 200 to 400 billion stars. These things contain 1,000 times that energy, and it's beaming right at us. And so we can see it, use it as a background source for many different experiments. And it's the other reason that it's quite nice is that its spectrum is bright. And in particular, it forms a nice background continuum at ultraviolet wavelengths. So there's a lot of light coming from the quasar at the exact wavelengths where we want to be looking at absorption. And so Another thing I want to mention is this most prominent feature here. So I've labeled that Lyman alpha. And it turns out that since hydrogen is the most abundant element in the universe, the spectrum of hydrogen is particularly important. Emission or absorption processes in hydrogen give rise to series. Some of you may be familiar with the Balmer series or the Lyman series. The Lyman series, because of the atomic structure of hydrogen, emits in the UV, so that when a hydrogen atom absorbs a photon with a specific energy, the electron gets excited from the first state to the second excited state. The Balmer series is from the ground state, if you're familiar with that. But in general, these series, right, these different levels, produce different transitions. So the Lyman alpha transition is at 1216 angstroms. This is in the ultraviolet, right? And then the Lyman beta transition to the next excited level is at 1026 angstroms, and then you could go down, Lyman gamma, etc. And there are all these series that are fairly easy to identify. They produce this very nice absorption signature in a galaxy. So again, I'll remind you the intrinsic spectrum of a quasar. This is what you would see. Say you're at the quasar and you just take a spectrum just directly of the quasar. But actually, in reality, when you look at the spectra of quasars, this is what they look like. And so you've got this Lyman alpha line now redshifted because the quasar is very distant. And you've got lots of absorption features. And these are all real. This isn't noise. The spectrum is pockmarked by a ton of Lyman series absorption. And so you can identify these different absorbing systems at different redshifts by noting their Lyman series. For instance, here, this is a damped Lyman alpha line, and there's Lyman beta, Lyman gamma, etc. And you go down the series, you identify that, you know Lyman alpha then is redshifted here, and so that's a system in the foreground of this quasar that you're looking at. And you're looking at its absorption spectrum, its Lyman series. And in this particular quasar spectrum, there are at least 3 different foreground systems that are being probed. And so just to give you a better idea of exactly what it is I'm looking at, I have this video here. And so what you can see, this is again the intrinsic spectrum from a quasar. This is this Lyman alpha emission line from the quasar. Now this is at 0 redshift. We're at the quasar starting out. And you can see here are metal ions as well. So you can see Lyman series at a particular redshift, but then there are also ionized carbon, silicon, and various ionization states. And so I want you to watch as we move away from the quasar and the light ends up passing through some intervening clouds, and watch what happens to the spectrum as it does that. And so the light's going to keep going, and you see that there's some Lyman series. Each time it goes through a cloud, you get a new Lyman series. This is called the Lyman alpha forest, right? And then all of a sudden we're going to pass by a galaxy. Boom, you've got a DLA, a huge series. You've got some metal lines in there when it passed through that. And so that's ultimately the kind of experimental design that we're forced to deal with because our instruments are not sensitive enough to detect this gas directly by its emission. And so we have to use these background absorption line experiments using quasars as our background illuminating source. And so back in 1969, 2 very famous astronomers, John Bacall and Lyman Spitzer, wrote a seminal paper in which they predicted that most of the absorption lines observed in quasars with multiple absorption redshifts are caused by gas in the extended halos of normal galaxies. Now, this prediction has taken a while to be borne out. I guess, almost 50 years later, here we are, and I think that we now have the tools sensitive enough to be able to at least test this prediction. And so if you're going to design an absorption line experiment, there are 2 ways that you can go about doing it, okay? So here you go. You've got a bright background quasar here. This isn't a very impressive, this is from the Sloan Digital Sky Survey, right? And you can identify this as a quasar from, various spectroscopic experiments or colors, but you have this bright background quasar and you know it's redshift, okay? You have a spectrum of the quasar and you have absorbers in this quasar spectrum at different redshifts. And so if you want to understand how the gas relates to galaxies, you can first of all, take the absorption redshifts and go hunting for galaxies at those particular redshifts, right? You can say, oh, look, I've got a Lyman series at a redshift of 0.2. Let's go hunting for a galaxy at 0.2 that could be responsible for that. Now, that might bias you in a particular way toward galaxies that always have absorption. So if you wanted to do an absorption blind survey, what you might do is instead, you know the redshift of the quasar, and you roughly know the redshift of galaxies that are in the foreground, just from their colors. You can say, roughly, this is at about 0.2. And so you get these images where you get quasar-galaxy pairs, and you know nothing about the absorption toward the quasar. And then what you do is you go and take spectra of the quasars, and then you go hunting for absorption at the redshift of the galaxy. And so that's how we've designed this particular survey. I've done an absorption blind survey to try to understand, in general, the properties of gas around galaxies. Is it there all the time? How frequently do we observe, say, hydrogen around galaxies? This is something that nobody had observed until very recently. And part of the reason that nobody has observed that is because instruments weren't even sensitive enough to detect this particular gas in absorption until very recently. And so in 2009, you guys might be aware that there was a resurfacing mission to the Hubble Space Telescope. If you saw the movie Gravity, where Sandra Bullock is up there, fixing the Hubble Space Telescope, the astronauts actually went up there and they installed this new spectrograph called COS, the Cosmic Origin Spectrograph. This is a spectrograph that is sensitive to ultraviolet light, and in particular, it's over 10 times more sensitive to ultraviolet light than any previous ultraviolet instrument in the history of astronomy. And so all of a sudden, you're able to select quasar-galaxy pairs in this way. There's no way you could have done an absorption blind survey previously just because there are too few bright quasars on the sky. So you wouldn't have been able to get a good enough sample to do this. But finally, with the Cosmic Origin Spectrograph, you can get a sample where you get quasar-galaxy pairs, and there are enough quasars that are bright enough to observe with the Cosmic Origin Spectrograph. And so that's what we did. We observed 39 quasar-galaxy pairs, and with known galaxies in their foreground, with targeted galaxies. We have actually 51 targeted galaxies. These are a mixture of both non-star forming red galaxies and star forming galaxies, because we also wanted to understand if the halos of these galaxies that are no longer forming stars look fundamentally different from the halos of galaxies that are forming stars. We might expect that they would, just because the gas physics are so fundamentally different in these galaxies. I've done this work as part of a team. We call ourselves the COS-Halos team. This is a rogues gallery of some of the scientists involved in this work. In particular, the PI, Jason Tumlinson, is pictured here. He's at Space Telescope Science Institute. And X, the astronomer formerly known as Jason at UC Santa Cruz, with whom I work very closely. And then a whole slew of postdocs and grad students and professors at other institutions. And just to illustrate to you that the whole entire universe opened up with the Cosmic Origin Spectrograph, and so this is another plot that I've drawn just to show you how much of a game changer the Cosmic Origin Spectrograph was. So these are the quasars in the sky that were able to be observed before the Cosmic Origin Spectrograph. This is their brightness here, their apparent brightness. So that all of the quasars fainter than this limit here were off limits to any previous instruments. But then all of a sudden, with the installation of COS, we have all of these quasars at even higher redshifts that we can now use as background sources to study gas in the foreground. And so here's some snapshots of the quasar-galaxy pairs that are part of our survey. And what you can see is a lot of times we just had one targeted galaxy, but sometimes there's another galaxy that also happens to be in the foreground at a totally different redshift. We call those bonus galaxies. And what we're doing effectively, because we're limited to one sightline per galaxy, what we do is we select based on galaxy properties. And so what we did is we selected galaxies that had roughly all the luminosity of the Milky Way. We selected galaxies all at a particular redshift, at Z of 0.2. So this is maybe, a billion galaxies a billion years ago or so. And we selected within this redshift range and this luminosity, we're looking out a certain distance into the halo. In the rest frame of this galaxy, this quasar has to be within 150 kiloparsecs of the central galaxy. So we're looking at gas within 150 kiloparsecs of the galaxy. Now to orient yourself again, remember that the disk of a galaxy, the star-forming disk, is about 20 kiloparsecs. So we're going out quite a bit further than that into the halo of the galaxy. And so ultimately what we're doing is we're creating a kind of statistical map of the halo with a single sight line per galaxy, but we get galaxies at all different, what I call impact parameters, okay? So we get some galaxies very close in, within 50 kiloparsecs. We get the gas around some galaxies within 100 kiloparsecs, some, out to 150 kiloparsecs. And so in this sense, we can understand how the gas physics changes as a function of how far away from the galaxy you get. And so this is our kind of statistical map of the halo. And in lieu of being able to take a direct image of the halo gas, instead we can just kind of compile them all into a picture of what the halo gas is doing. And so now I'm going to show you some of the results. And like I said, we've designed this experiment in the following way. So we have a quasar here, we have a galaxy here. We know the redshift of the galaxy because I went to the Keck telescope in Hawaii and I took a spectrum of the galaxy. And what you can see is this is a spectrum of a galaxy that's forming new stars. And so a lot of the light being emitted is the light from the gas around these new stars. And it has an emission spectrum. And luckily, when you have an emission spectrum, this line right here is the hydrogen alpha line, for instance. So this is part of the Balmer series, which is in the optical. And you can see this hydrogen alpha line, which is normally at 6562, has been redshifted to 7,500 angstroms. You can get a redshift of the galaxy, which gives you a recessional velocity of the galaxy. And so then you know precisely where you need to look in the spectrum of the quasar for the Lyman alpha absorption. You know where this Lyman alpha line is going to exist if it's in the halo of the galaxy, because you know what redshift to expect it at. And so you go hunting in the spectrum of the quasar, the COS spectrum of the quasar, and at the redshift of the galaxy, and here you go. Okay, we find very strong Lyman alpha absorption in this particular quasar-galaxy pair where we're looking 15 kiloparsecs into the halo. Okay, here's another one. Now, we have a spectrum of a galaxy. We go hunting in the spectrum of the quasar for Lyman alpha absorption. There it is. Here's another one. We go hunting. Here it is. Here's another one. Okay, so now I could do this 51 times, but in the end, the result is that every time we go looking for Lyman alpha absorption within 150 kiloparsecs from a galaxy, we see it. So that means this hydrogen around galaxies, this diffuse hydrogen gas, is ubiquitous around galaxies, at least out to 150 kiloparsecs. Now, the interesting thing about this is I told you that we have blue star-forming galaxies and red Narn-star-forming galaxies. So galaxies are forming stars because they're able to accrete gas, right? And some people, a lot of astronomers, until this result came out, thought that one of the reasons galaxies are not forming stars anymore, that there's a significant population of red galaxies, is because they have no gas left to accrete, right? They're not drawing on any reservoir of gas. But what we've shown here is that's not true. And in fact, there's just as much gas, there's a gaseous reservoir that's just as large around red galaxies as there is around blue galaxies. So for some reason, maybe that gas isn't falling onto the galaxy and able to form stars, but that gas is there. And so that was one of the first surprising results. The second surprising result is how much gas there is. And so that's what I'm going to get into in a bit. Exactly how much gas is there, how much mass, how much baryonic mass in this diffuse gaseous component that's very extended is there. So, like I said, we get lines from Lyman alpha, the Lyman series, Lyman beta, Lyman gamma, etc. But we also get lines from ionized metals. So this gas isn't pristine gas that has never seen the byproducts of star formation. So, right, I told you before that the way we think heavy elements are generated, at least elements heavier than helium in the universe, is from fusion in the cores of stars. The fact that this gas exhibits carbon, nitrogen, magnesium, silicon, all in the same ratios as we observe them in normal star-forming environments, indicates that this material has been enriched by the byproducts of star formation. So this material has probably come out of a galaxy at some point. It was in a galaxy at some point, and now it's kind of in the halo of the galaxy, and who knows what's going to happen to it. The gas, the other thing that I want you to recognize, and so this is just one spectrum, right? And now I've centered it on the rest frame of the galaxy. So 0 kilometers per second corresponds to how fast the galaxy is moving. The other thing is that most of this gas, when you talk about escape velocity from the halo, you could think maybe this gas isn't even in the halo. Maybe it's not associated with the halo. Maybe it's in the intergalactic medium. But most of this gas is well within, 100 kilometers per second of the galaxy rest velocity. So what that means is the escape velocity from a galaxy of this luminosity is over 300 kilometers per second. So we're seeing gas that is bound to the galaxy's halo. Okay, so now I'm going to talk about this one particular problem that we think we've solved with these data, and that's what people were calling the galaxy halo missing baryon problem. And I already introduced this to you before, but I'm gonna cement these ideas into your head. And so what you've seen here is probably something that you've seen before. This is a picture of WMAP, and this measures the very small differences in temperature of the Big Bang's relic radiant heat of the cosmic microwave background. And so it turns out that the early universe was highly uniform and homogeneous mix of both dark matter and baryonic matter. And it's one of the greatest triumphs of cosmology that we know this fraction very precisely. It's 17%. 17% of all the gravitating matter in the universe is baryonic in nature. That is normal atoms, like in your body. And 83% of that, by mass, is dark matter, which we don't know what it is. We're slamming particles together in Switzerland to figure that out. But in general, this fraction holds this universal baryon fraction. But as far as a galaxy is concerned, right, it has a dark matter halo, and you know precisely how much dark matter is there from various measurements. Say, take a rotation curve. Then you can count up all the stars in the galaxy. You can count up all the gas in the galaxy disk, and you're not even close to being at that cosmological fraction, right? You're only at about 5 to 10%, okay? So you're missing over 70 to 80% of your baryons compared to this cosmological fraction when you add up all of the known components. And so this is what people have called the galaxy halo missing baryon problem. But all of these people that were studying this problem weren't looking for gas in the ultraviolet in the halos of galaxies. And I just told you that we find a lot of it. So people were proposing that maybe these baryons never fell in the first place, that the baryons might be in the intergalactic medium, or maybe they're too hot, too highly ionized, and we're not detecting them. People also talked about missing metals in galaxies. So one of the results to come out recently is that you add up all of the metals that you expect to find in a galaxy, because you know the rate at which it's forming stars, you know its stellar populations, its current stellar populations, and so you know how many metals it would have generated over the course of its life, right? And so you have an expectation for that, but it turns out that when you measure the amount of metals in a galaxy, it's something like 80% less than the amount of metals that they would have generated over the course of their lives in the interior, from the stars ejecting in supernovae to their interstellar medium. And so these metals are missing. Well, where are they? Potentially in the halo. And so there are these two problems, a missing metal problem and a missing baryon problem. So first, let's talk about the missing baryon problem. So I told you before that we detect hydrogen from the Lyman alpha, the Lyman series, in all of our spectra. There are a few non-detections, but let's ignore those. So what you see here right now is the equivalent width of Lyman alpha. This is just a measurement of the strength of the absorption feature that you detect. Now this is impact parameter from the galaxy and the rest frame of the galaxy, so it goes up to 150 kiloparsecs. And this is just another way of representing those data to you. The blue squares are the sight lines around blue star-forming galaxies, and the red triangles are those around red galaxies. And so this is showing you what I was showing you before, that hydrogen is ubiquitous around galaxies out to 150 kiloparsecs. you can actually then turn this into a column density, which is a slightly more physical way of representing how much gas is there. And this is just the number of atoms per centimeter squared, because you're limited to this kind of pencil beam through your gas. And so what you find is the distribution of this gas, and you get a lot of lower limits because it's saturated. But what you really want, if you want to know how many baryons are there, you don't just want to know about the neutral hydrogen, because I told you that the gas is ionized, right? So most of the hydrogen isn't going to be in H1 observable via the Lyman series. And in fact, there are no, unfortunately, because the universe is tricky like that, there are actually no transitions of ionized hydrogen that we can look at. And so instead what we have to do is we have to use the ionized metals that we saw in the spectra. And so right here what you can see is we've got silicon 2, silicon 3, we've got carbon 2, and we've got carbon 3. And what you can do is you can take the ratio of these different ionization states of these heavy metal lines to determine the ionized fraction of gas. What fraction of the gas is ionized? And that gets you the fraction of the gas, the fraction of the H1 that is ionized. And at these temperatures, we expect most of the H1 is ionized. Okay? And we go through every sight line and we very precisely determine the fraction of hydrogen that's going to be ionized. And we make a correction then for total hydrogen. And this total hydrogen is going to then be able to get us a total baryonic mass, because 99% of the mass in gas is in hydrogen. So here's our total hydrogen column density after we correct our neutral hydrogen column densities for this ionized fraction. And so what you see here is 10 to the 20 or so atoms per centimeter squared of neutral hydrogen extending out to 150 kiloparsecs. I'm now parametrizing this by the virial radius, which is just a total dark matter radius, but imagine this is 150 kiloparsecs, that's the same. And so how does this compare now? Like I told you before, these galaxies are missing a lot of their baryons. Now let's take this as like a surface density, integrate it out, and then determine the mass of gas in this circumgalactic medium. And we can do this. It's a very rough estimate. And actually, the way that I did it is very conservative. And so what I did is I placed a lower limit on the amount of material that can be there, because a lot of times our hydrogen is saturated, and then I make very conservative assumptions about this ionized fraction. And so now I'm just going to show you a bar chart as to where we are on the baryon census in the halo of a galaxy. And so what you see here is the disk of a galaxy gets you maybe to 25% if you're lucky. And the cool CGM now, there's an additional at least 50% of your baryons that you're going to get. So it's a huge amount of material in this gas around galaxies. And also there's what we think is probably a different phase with more highly ionized species. There's even more in this hotter component of the circumgalactic medium that we can't measure well. So if we take a census of all this material, there's also X-rays, but we don't think that they contribute very much to this gas. So, but in general, you get to the cosmological baryon fraction. So this missing baryon problem around galaxies is solved, I think, when you consider the diffuse gas in the halo of the galaxy.
Why is some of it dark and some of it chill?
Yeah, that's a good question. So in my paper, this is a plot that I grabbed from my paper, I make two different estimates, two different conservative estimates that are lower limits. And so the lowest one is assuming, so we've got a hydrogen saturated Lyman alpha line, say. We assume that saturated column density that we get, which could be a lower limit by more than an order of magnitude, is the actual column density, and make a correction to that. So that's like a factor of 10. And then this one, we do a kind of correction for that saturation with void profile fits, and so we take that fitted column density, which is actually still a lower limit from the other assumptions that I made. So but I thought it was a more realistic lower limit, and so I put that one there as well. And so that brings me to the end of my talk. And there's a lot more to do, and there's a lot more that we can do with these data. And in particular, we can look at the origin of the gas, we can look at how the gas is moving with respect to the galaxy, the so-called kinematics of the gas. We can get metallicity of the gas, figure out how enriched it is from previous generations of star formation, what fraction of the gas is coming from outflows versus inflows. I work with simulators on answering some of these questions. How much of the gas is coming from an intergalactic component. how ionized is the gas? All of these questions are things that I'm interested in doing, that I have ongoing surveys to look at, but I thought that was a good introduction to my research. All right, thank you.
Before we go into some more extended time for questions, I think we have time for a couple of questions right now. Yes?
What would happen if you went to 200 kiloparsecs?
There's still gas, actually. People have tried to figure out the extent of the circumgalactic medium, and it looks like, it's really weird, but it looks like 300 kiloparsecs is a cutoff. And it's totally regardless of what the virial radius of the galaxy is, what type of galaxy or whatever. It looks like at high redshift, at low redshift, it goes out to 300 kiloparsecs.
I'd like to ask a question. So that was my other question, which was, it seems like you want to figure out what the extent is and work backwards from this. My question is, how would you phrase this in maybe just 2 sentences? I'm making it hard for you. Because in essence, this is a missing matter that you found, right? And so how would you, in a couple of sentences, tell the physics, to the physics students and the other students, like, what is it that meant it was hidden from us for all of this time? I mean, it's there in your talk, but that's something that kind of left me, as I thought about it, it's like, this is a great mystery and you've solved the mystery. How would you quickly go to say to someone, oh, this is why there was this mystery that I solved?
Yeah, it's because you can't see the gas directly. It's so diffuse. I mean, you think of the density of air, it's probably like, it's approximately, 1 million times greater than the density of this gas. So it's like you're looking through, you can see everything through this stuff. It's like, it's transparent, basically. So you have to design an experiment looking for it specifically. There's no way to just, happen upon it. And actually, one of the ways in which it arose was because you look at every time you look at the spectrum of a quasar, there's all this absorption, right? That's in the foreground of the quasar, and you're like, what in the world is that coming from? And so you have to do these kinds of, absorption line experiments, and specifically to get at this component, there are not very many quasar-galaxy pairs that you can study in the universe. So you have to really work hard to get, a well-designed experiment to actually detect it.
That's good.
That was more than 2
No, that's good. I wanted that. I'd like for us to continue with questions. I especially appreciate the people who stayed quietly in their seats for our question section. We have another 15 minutes of question section, which I'd like to do. Some of you have other classes, and if you do, I'd like to ask you to excuse yourself quite quietly and quickly right now. And we'll continue again with questions in 1 minute.
In the interstellar medium of the galaxy disk, and so it's been enriched in metals from winds from the massive stars that are generating the metals, or after, say, a supernova. But this is gas that has just been enriched by many cycles of star formation happening within it, and then for whatever reason, we think, during the death of a star in a violent supernova, some of this gas is ejected from the disk. It doesn't escape the halo of the galaxy, but it gets ejected into this halo. And so I think most of the gas that we're seeing has been enriched in metals, and so most of the gas is probably a product of this outflow.
It has kinetic.
Yeah. Oh, yeah, for sure.
So you've measured, you've determined that there's gas within this 150 parsec radius of the galaxy. So and it's bound to the galaxies because that's also flowing in. Do you have any information, or what do you think about gas or matter between galaxies that's not bound to galaxies?
Yeah, absolutely. The intergalactic medium is, a new frontier, happening right now. It's at the forefront of research, and I work with people at UC Santa Cruz to look at this. And so you can probe the sort of filaments, right, the gas between galaxies in the same way, using quasars as background sources, but you design the experiment very differently. You don't want to necessarily look near galaxies, because then you're going to be looking at this circumgalactic medium, which really dominates. The intergalactic medium is way less dense than even the circumgalactic medium. And I would say there's no yet definitive detection of the intergalactic medium. Even though we know it has to be there, there are putative detections, and I think that there's exciting stuff happening right now in that field. But one of the hardest things about the intergalactic medium compared to the circumgalactic medium is this might not be gas that's as enriched, right? So it doesn't have the metal transitions. There are way fewer transitions to look at, and the gas is way hotter, so that when you look at the hydrogen, the Lyman alpha, it's very broad, it gets smeared out, spread out, so you need very high signal-to-noise data to get it. And so it's even more difficult than this.
And will the James Webb Telescope help? Or
it will help for very high redshift things. The James Webb Space Telescope is an infrared telescope, so that's at very different energies. But there are other missions that are being proposed now, just medium kind of ultraviolet missions that'll be better for it.
Yeah, here, you have a question? Oh. Yes, Lauren.
Could you tell me about the shape of the nebulous?
That's a great question. And actually, that is something that I'm doing right now using adaptive optics. And so one of the things that people think might be happening with the shape of this gas is that when you look at winds close by to a galaxy, you always see them in like a biconical kind of structure where, they're probably coming out mostly from the center, and then they're being ejected, and they have these like opening angles. And so they think that most of the gas is going to be distributed along the minor axis of the galaxy that's, consistent with this outflow kind of picture. And so right now I'm doing that. We can't do that with the data that we have right now, because we need the exact inclination angles of the galaxies in order to figure out what shape the gas is. But we're getting those with adaptive optics, which you might know something about, and many high-resolution images of the galaxy, and we're trying to figure that out right now. And I can tell you from the few sightlines that I've done already, it is consistent with this kind of, biconical outflow picture.
It's very fun. I have another question. I'm going to jump in. Back to this, when I think of whether it's Via Lactea or other simulations, there's simulations on, I think it's Hopkins' work or something on AGN.
Yeah. And
so what percentage of this enriching gas has to do with the supermassive black hole? How much has to do with many supernova going on?
Wouldn't we love to know the answer to that question? I don't know. I can say though, it's hard to tell whether or not any of these galaxies have ever had an AGN, right? We think the active period of a galaxy is kind of short-lived, right? Like when it has an AGN, you're just seeing this kind of brief window over which it's been active. And so all of our galaxies that we can tell are not currently the hosts of an AGN. Whether or not they were at any point in their history, we don't know. But people are actually actively looking at that by studying samples of AGN and quasars, but they're way harder to come by because AGN are rare, and then the background quasars are rare. And so they're different experiments just in different regimes. But I would say that some fraction of this material has to be related to the black hole. But I think probably the majority of it is a more commonly ejected material from star forming processes.
Yes.
Is the distribution of the circumgalactic gas uniform, or is there some structure to it?
That's also a great question, and that's one question that I think higher resolution will let it. But the way that most people think about it is that it's that is clumpy. And so they're kind of large clouds, with a low volume filling factor, but they're massive clouds containing a lot of gas. That's the way that people think about it. What we see is roughly consistent with that picture, with the kind of, when you look in velocity space, there's this component structure, and usually if you go higher resolution, there's more and more components, so it is kind of this like clumpy structure, we think.
Any more questions? Well, let's thank our speakers.